Hello, everybody. Welcome to Lecture 9, Linear Regressions. Excellent. So I know we jumped around a little bit on the syllabus, but we're going to continue with our parametric model series. And I'm really excited for today's lecture because this one is taking stats, making it really, really applicable. I think that in a different way, this is almost a kind of data science way of leveraging data. You know, prior to this lesson, everything that we've learned about has been kind of proving hypothesis, confirming if there are differences, identifying which differences are in the group and such. But what linear regression is actually going to do is, instead of confirming if there are differences or not, we're actually going to leverage this to make predictions, right? And to take information that you collect and then make inferences, right? Make predictions and make inferences on and based off of the items that you have collected, right? So I am really excited about this lecture, and we are, in fact, really light on SAS. I mean, I wouldn't say we're really light on SAS, but you know, there's a little less SAS, a little bit more Excel, but we will get to that when we get to that. Let's go ahead. Let's do a quick review, right? At this point, let's take an honest assessment of ourselves right now. You should know the 3 t-tests that we went over. You should know ANOVA, and you should know all of the assumptions of parametric tests and how we essentially test for them, right? So you should know when you would use a one-sample t-test, when you would use, or the differences between a dependent and independent t-test. You should know when to use ANOVA, and then you should be able to go ahead and make a decision and determine which group is different from the other groups, right? So these are really important things that you need to have grasp of right now. And let me just fix these right here on these slides. T-test. You should have this understanding. If not, you know, ANOVA and the assumptions, these are all recorded, the t-test we did in person, but you know, it's time to go ahead and kind of really review your notes and get down with this one, right? And get a strong understanding with this, because now we're adding in linear regression. This is really starting to slope upwards and pick up, right? But have no fear. What we're going to do next class we are in person, right? And what we are going to do is we're going to have just a series, a whole bunch of different case studies. And ultimately what you're going to do is, in small groups, work through these case studies and then present them to the class, right? So I'm really excited about this. I think that this lecture is going to be a lot of fun. We're going to do the same thing that we've done before, which is we're going to cover what the assumptions are, but we're not going to do any of the testing for the assumptions, right? We're going to go over what the assumptions are of linear regression, but then what we will do is just make the assumption that we're going to assume that all of the assumptions have been met. And then next week, before we go ahead and do our big powwow, we'll go ahead and we'll learn on how to actually test for those assumptions and follow this same convention that we did before. Okay, so very good. Bear with me, take a sip. And let's begin. So, what is linear regression, right? Linear regression is a method for analyzing the relationship between 2 quantitative variables, x and y, okay? So quantitative variables, these are our continuous measures, right? Our continuous numbers right over here. Linear regression is a useful statistical method we can use to understand the relationship between 2 variables, x and y, okay? And when you think about linear regression, just remember the first word is linear, right? There needs to be a linear relationship. So when you think about a linear relationship, the most classic one that I want you all to think about, because it's most applicable to you, is height and weight, right? Let's just think about this one for a second. Height and weight. What do you expect to happen with weight when you increase height? Well, you expect weight to increase as well, right? As height goes up, weight should go up, and that's a linear relationship right here, right? So you perform a linear regression, when there is a linear association with your two variables. So we had just said height and weight. Here's another one: calories consumed versus body weight, right? So if somebody were to eat a 800 calorie diet, you would expect them to weigh less than someone who ate a 8,000 calorie diet. Am I right? Another example could be hours spent studying versus exam scores, right? So somebody who studied 1 hour for the SATs is probably not going to score as high as someone who had studied 35 hours for the SATs, right? So I hope that makes sense right over here. Now, regression analysis is commonly used for modeling the relationship between a single dependent y variable and one or more predictors, right? We'll come back to this slide in a second. Let's just work through this one right here. When we have one predictor, we call this a simple linear regression, right? And our expected y is equal to the intercept plus the first coefficient times x. Don't get hung up on the math. It's actually really easy. You might have heard of y equals mx plus b, right? Your b0, this is your slope right here. Y equals slope. This is the m, right? And this is your b, okay? And then when we have more than one predictor, we call it multiple linear regressions. I know that this one seems a lot, and you might be a little nervous. I promise you, right? And I haven't, I don't think that I've let you down yet. This is actually not as complicated as it seems, right? So I think that this next slide that we're going to go to is going to really help explain it. So this is what we call a scatter plot, right? We have our y-axis, and let's just say our y-axis here is height. And then we have our x-axis here on the bottom. Follow my mouse, folks. The x-axis will be weight, okay? Here it says in the figure, the thing we want to explain, height, our independent variable x, the factor we think might influence the dependent variable, y, right? So remember, height and weight. Now these are our data points right over here, okay? So each point is a person. And what you're going to see is, look, this person on the y-axis is pretty short. And guess what? They weigh not that much, right? So this might be 80 pounds here. And this might go all the way up to maybe 250 pounds. And maybe this is 4 feet. And it goes all the way up to 7 feet, right? Let's just pretend that that's the case. So now you have someone here that's maybe around just under 5 feet and weighs just under 80 pounds. Does that make sense, right? So just make that imagination. Now look, just imagine that. Now as you see height increase and weight increase, you'll notice that there's this relationship right here. And then this line is called the line of best fit, right? The line of best fit, if you only had data in x, this would provide your best estimate of y. Okay, so this line is exactly through the middle, this very, very, very middle of all of these points right over here. Okay, let me just say that again. This is called the line of best fit, and it is the middle of all of these points right over here. And if it draws a line going this way from bottom left to top right, or if it goes, this is a positive relationship, or if it goes from top left to bottom right, and goes this way, that would be a negative relationship, okay? Then we have our r squared value, and you'll see that the r squared value here is 0.77, right? That is the variance in y explained by x. Remember this. This is very important. If it's lower than 30, it means they're not connected. There's no correlation. There's no connection here. Above 95%, and it's practically, they're all sitting on the same line. Anything above 0.7 is pretty good, okay? Anything above 0.7 is acceptable right over here. We're going to circle back to this slide in the future and talk about confidence bands, but we're not going to talk about that right now for today. So let's go ahead and let's really try to understand this for a second. And I'm going to see if I can go ahead and draw a picture. Let me see. Here we go. So let's say hypothetically, you didn't know, all you knew was somebody's height. And you wanted to make a guess in terms of what their weight was, right? So let's say right here is 5. Oof, that doesn't work. Hold on. Let me undo that. Let's say this point here is 5 feet, 10 inches. Wow, really hard to draw. And then, so let's say this right over here is 150, right? And this is 250. And this is 80, right? And this is 4 feet. And this up here is, let's just say here it's 7 feet, okay? 1, whatever. So, this is ultimately how linear regression works. If we have our data looks like this, it's linear, we draw a line of best fit, and our R value is above 7, then that means chances are we're able to go ahead and run a regression analysis, right? So if you had 2 continuous variables, 2 numeric variables right over here, you could plot them, and if they have this relationship, you can say, look, I have somebody who's 5 feet 10. I think I can guess what their weight is going to be, right? And I'll do that by going like this, going across, finding this line, and then coming down. And you'll see that we'll make the estimate at 150. Does that make sense? Right? This is essentially how linear regression works, right? And then now if I wanted to go ahead and say, let me make an estimate on someone who's 4 feet 5, I would go from here, I would draw this line up until this line of best fit, come straight down, and then I would say, this person weighs roughly about 90 pounds. And I'm very sorry for not being able to write a little bit neater here, but hopefully you get the gist of this, right? And in order to go ahead and figure this out, what we do is we apply this formula right here. Y equals intercept plus coefficient times the value, right? Y equals mx plus b. And that's essentially what's going to give you this, and that's in sum ultimately what linear regression is. Now let me see if I can clean this slide up for you all. Let me just undo. Okay, I'm going to undo a lot. Bear with me one moment. I'll try to give you a clean. Actually, you know what I'll do? Work smarter, not harder, right? Let me go ahead. Oops. Oh, that's why. Turn this off. Take this line, plop it here. Good. And then so this way, when I share this with you all, you're going to have a nice clean slide again. Okay, remember, so y equals mx plus b. What I'm saying here, most important takeaway, is we need this linear relationship, right? So let's come back now. So hopefully that goes ahead and explains this simple linear regression a little bit more. Then what we do is when we have more than one predictor, we call it multiple linear regression. And we can have as many predictor variables here as we want. And ultimately what happens is when you have multiple predictor variables, you have multiple lines of best fit. So for the time being, just concern yourself with simple linear regression. No need to go ahead and jump into multiple regression just yet, because we're going to go into detail on that in the future. All right? Great. So let's go over the assumptions. Linear regression has assumptions just like all of the other statistical tests and statistical methods that we perform. Okay? So first things first, the first one is linearity. The relationship between x and the mean of y is linear. Number two, I always have trouble pronouncing this, so bear with me, but homoscedasticity, I think I did well there. The variance of the residuals is the same for any value of x. So another way to put it is that the variance of residuals are approximately equal for all predicted dependent variable values, right? Independence, the observations are independent from each other. You see that that's very similar. Normality, for any fixed value of x, y is normally distributed, right? So again, this sounds familiar from our t-test and ANOVA days, right? That our data needs to follow a normal distribution, and we would test for it in a very similar way. And little or no multicollinarity, right? And I'm going to save this one for a future lecture, so I'm going to take that out of there, and you won't even see it in your slides right over here. Okay, great. So, assumption number one, linear relationship. The first assumption of a linear relationship is that there is a linear relationship between the independent variable x and the independent variable y. We test for that by creating a scatter plot, and that allows you to visually see if there's a linear relationship between the two variables. If it looks like the plots fall in a straight line, then that means there is some sort of linear relationship, right? And then you go ahead and calculate the r-squared value, and like I had mentioned before, if it's greater than 0.7, then you're good to go, right? If it's greater than 0.95, then you're practically on the line. So let's go ahead and take a look at an image here. This one on the left, this is a linear relationship. You can clearly see that, right? But this one on the right, this is not a linear relationship. So if the data looks like this, you're not really going to be able to go ahead and perform this relationship. Well, you could, but you're just not going to get anything meaningful from it, right? Remember, the way that linear regression works is we put in the line of best fit. It fits good. We're tight along this line. We have a high r-squared value. And then what you do is we know y, we know someone's height, and that'll estimate somebody's weight from there. Okay? Our second assumption, independence. Independence means that there's no relationship between the different examples, right? This isn't something that you can do by looking at the data. What you need to do is you need to know how the data essentially was collected, right? So let's pause for a second here. How do we know about independence? Let's think back to our previous classes. I'll give you a hint. There's a couple of different ways to go ahead and set up these data collection protocols. All right, so take a second. And if your answer was the different types of study designs, you are correct, right? So was it a simple random sample? Was it a clustered sample? Was it systematic, etc., right? So a clear case of independent observations, which is what we want, are experimental studies in which participants are randomly assigned to treatment groups. In this case, it is the fact that the assignment is random and there are no hidden relationships between the observations. Okay? Very good. The next thing that the next assumption that we're gonna look at is homoscedasticity. I think I got that right. The next assumption of linear regression is that the residuals have a constant variable at every level of x, right? This is what is known as homoscedasticity. When this is not the case, the residuals are said to suffer from heteroscedasticity, right? So again, we're going to go more into this one, and I'm going to practice how to pronounce these a little bit more. But ultimately, what you need to go ahead and do is to check for homoscedasticity is by running the White and Pagan test. And you run the test, and you set your null and alternative hypothesis. And ultimately, what you want is to see that there is no difference in your null, and that it's greater than 0.05, right? Then you're good to go. Again, we will go into depth on this one in a future lecture. For this lecture, our assumption is that all of these assumptions are just true. The fourth is normality, okay? And in class, we had asked, hey, listen, what are all those pretty figures that SAS generates out for us right over here, right? Some of those figures are known as the normal probability plot, or a PP plot, or a normal quantile plot of residuals, or a QQ plot. So if the distributions are normal, the points on such plots should fall close to the diagnostic reference line. A bow-shaped pattern of deviation indicates that the residuals have excess skewness. And then an S-shaped pattern of deviations indicate that the residuals have excess kurtosis, right? Which means there are too many or too few errors in both directions right over here. Again, just know the assumption. We're going to go into depth on this one, but just to give you a sneak peek, what we are looking for, it's curious that I have bad and good reversed. All right. I should have good on this side, and then bad on the other side. So here we go. So you'll notice that good normality, notice how we have a reference line and all the points really kind of fall onto this one, right? And then a bad, or assumptions are being violated, you'll see that it kind of looks like an S, right? You see how it curves this way and then it curves the other way? That means we are violating that assumption right over here, okay? Just like we did with t-tests and ANOVAs and other parametric tests, visual inspections aren't always the best. So sometimes what we'll do is just statistical tests, right? Where it gives us a concrete number and we just pick a threshold and draw a line. So you'll see that there are a variety of statistical tests for normality, including the Kolmogorov-Smirnov test, the Shapiro-Wilks test, the Yarborough test, and the Anderson-Darling test, right? And bold is Shapiro-Wilks because you should be very familiar with that one. Pause, and if you're saying, I never heard of the Shapiro-Wilks test, then you need to go back to some previous lectures and double check, right? This will be on the exam, so just a quick heads up, know that, right? But ultimately, the Anderson-Darling test is considered the best for addressing normality in a linear regression situation. But we will go ahead and do this, like I mentioned, in the future, okay? So things to be really mindful of and things to watch out for. Outliers, leverage points, influential observations, okay? These are the big key points right over here. These items right over here essentially go, you may have a linear relationship like this or like this, but then you may have a point that's really, really far out. And if you go ahead and you take a look at this point right over here, and let me zoom in, that is your outlier because it's way outside. And because this is here, this drags your line of best fit a little bit lower, right? Then what you have are things like your leverage points, and your influential observations, right? So let's go over each one. An outlier is defined as an observation that has a large residual. In other words, the observed value for the point is very different from the predicted by the regression model. Okay? Then you have leverage points. A leverage point is defined as an observation that has a value of x that is far away from the mean of x. So it's not an outlier, but this one value is very, very far away from the average. Okay, that's called a leverage point. And what you want to do is when you get really in depth into model building, you need to identify all your leverage points and make a decision. Does this really belong, right? And then influential observations. An influential observation is defined as an observation that changes the slope of the line. So an influential observation could be an outlier. It could be a leverage point, right? Thus, influential points have a large influence on the fit of the model. One method to find influential points is to compare the fit of the model with and without each of that observation. So let's come back to this slide right over here again. Right? I had mentioned that this outlier could be an influential point, right? Because this outlier might drag this model down a little bit. This point, though, however, it's not an outlier because it's within the confidence bands, but it can still affect this model fit. So sometimes you might want to just pluck these out and see how it fits and how it compares. Again, we're not that in depth just yet. We will get to that point. It's later on in the semester, but these are things to go ahead and kind of essentially watch out for. Okay. All right. Let's go ahead now and jump into our SAS exercise. Okay. You are a high school basketball coach. You're familiar with the adage, practice makes perfect. So you begin collecting data on the number of hours your students practice shooting and the number of shots made in the game. Using the shots.xlsx dataset, answer the following. Is the relationship linear? How do you know? What is the R-squared coefficient? Interpret this value. What are the values for B0 and B1? Write the formula for your linear regression model, and then let's make a prediction, or let's make an estimate. How many shots does your model estimate for shots? How many shots are, let me rephrase this, sorry. How many shots are made for a player that practiced 10 hours, okay? That's the question that we're going to go through this lab exercise, right? So we're going to use the shots.xlsx dataset, which I have here. And you will see we have a column, which is the number of hours practiced and the number of shots made. Let's just do a quick little observation, right? So we have one student who only practiced an hour, and he made 64 shots. That's pretty good, right? And then you'll see another student practice 2 hours, and he made 66 shots. And then all the way down the line, we have someone who practiced 14 hours and made 89 shots, right over here, okay? So let's go into SAS. You know this part already. We're going to upload the shots.xlsx dataset. The sheet name is called shots. We're going to do our running man and run them in. Notice all of our information is here. Notice that hours and shots made are our areas of interest right over here, right? Our columns and our column names. So the code is simple. Let me type this in, make some notes for you all. You used a prop reg, so you're going to have quite the collection of code now. Our table name or dataset name is linear, and we're going to model shots made equals hour. And let's go ahead and do our running man. Very good. Notice number of observations read, 15. Let's come back to our data set. You'll see that we have 15 values, and a quick way to go ahead and look is just to look down here. You see count equals 15. Notice it also gives you the average and the sum in this lower area right here. Okay, very good. So 15 is correct. Here is our parameter estimates. Okay, notice that our intercept is 65. That means our formula starts at 65, right? And let's think about that. Why does it start at 65? I'll give you a hint. Look at this data set. Okay? And now let's come back. Why does our intercept or our parameter estimate start at 65? So if you said the reason why it starts at 65 is because the lowest number here is 64, and the highest number is 89. And remember, we're going to predict how many shots are going to be made based off of the number of hours practiced, right? So the parameter estimate always gives you an indication in terms of what that value is going to be. And then here, what we have is the parameter estimate for hours is 1.98, right? So almost 2 shots per hour practiced. Okay, just think about it that way. And then now notice the p-value for both the intercept, which indicates the statistical significance of the model and the covariate, are both less than 0.05. So we know that this is statistically significant, right? Therefore, if we ran it 100 times, at least 95 times we would end up with ultimately the same result. Okay? And over here you'll see that the model is statistically significant up here as well. So now we have some diagnostic plots. Okay, notice we had talked about our QQ plot right here, or our residuals against our quartiles, and how it's fitted nicely to the line, right? No S-shaped curve here. Notice how our residuals are kind of follow a normal distribution here. Okay, and then residuals from shots made. What we don't want is a lot of spread. So notice our lowest value here is -4, and then we have a value of 6. They all kind of are evenly distributed in between on both sides. Notice right over here, we have a plot of shots made versus number of hours, right? And again, remember, what are we trying to predict here? We want to say, hey, oops, I just realized I made a mistake. Did I make a mistake? Yeah, I made a mistake. Okay, I'm gonna make this a 2-part video. My apologies.